Hello, this video is a supplement to your Lab 5, it's the San Andreas Fault and Earthquakes. So I'm going to go into the lab in a little more detail because it's a tough one. And I want to make sure that you guys are understanding this stuff because it is important. So let's scroll down here to plotting earthquakes. I'm hearing the most trouble from you guys with this section here. So basically, what they're asking you to do is to be the seismologist for the day. You're going to be the earthquake scientist, and it's going to be your job to locate the epicenter of a recent earthquake. So here is a diagram, and then here they have an explanation of a seismograph. So you as the seismologist, you have your station, right? So there's 3 earthquake stations. There's Bar, Glam, and Palm, right? So you can see those here. Those are your 3 seismographs. So one part of California, there was a station. At a different part of California, there's another earthquake station. And then maybe 300 miles away, another earthquake station. And each station is recording the compression, right? The waves felt by the earthquake. Okay, so what you're going to do is interpret those 3 seismographs from the 3 stations, and your interpretation will help you locate the earthquake epicenter. So when we look at this example here, right? This is the seismograph demonstrating the level of shaking, right? So before the earthquake, right, you have a flat line, nothing's shaking. But that first shake, right, the first shake you feel at the station, that is the arrival of the P wave. So remember in our earthquakes lecture, we talked about the difference between P waves and S waves, right? P waves move faster. They're always the first to arrive at a station. They can travel through all types of matter, whereas S waves, remember, they always come second, and they can't pass through things like liquid. And so what you're interested in, what you need to calculate here is the lag time between the first arrival of the P wave and the first arrival of the S wave. Because the reason you want to do this is where an earthquake occurs, right, depending on how close you are to the epicenter, this seismograph will look differently. So let's say you are right on top of the epicenter. That means your P and S waves would probably overlap. They'd be really close together. But the further away you are from the epicenter, the larger this distance between the P and S will be, right? It gets longer and longer and longer the further you are away from the epicenter. So we're going to use that relationship. We're going to be measuring this distance. We're going to look on each seismograph and say, okay, where's the first arrival of the P and where's the first arrival of the S? And then we're going to measure this distance and use that. So when we're looking for those, P will always be the first hit, right? From where it went flatline to where it started shaking, where you have this little wave here. The S wave isn't the next actual wave, but it's where you have a significant change in the amplitude or height of the waves being recorded by the earthquake station, the seismometer. Because S waves, shear waves, they are larger in amplitude. So when you try to locate the S wave, you look for the next part of the seismograph moving to the right that gets significantly larger in wave height. Okay, so now let's go look at our 3 stations, Bar, Glam, and Palm. All right, so here we have Bar. All right, so flat line, flat line, flat line, and then we have a shake. So right here at this spot, I'll go away. Right here at this spot, that's the first arrival of the P wave. Now I need to locate the first arrival of the S wave. So we can see here, this shaking stays at pretty much the same height, and then boom, it goes up. So that's the first arrival of the S wave, is right here. So our job is to measure the distance between the two. And notice here it's actually giving us time, right? Because remember, what this seismograph is recording is time, right? It tells you the time the P wave struck the earthquake station, and then it tells you the time that the S wave struck the station. So if we had to eyeball this, if this is 60 seconds here, right? This distance is 60 seconds. Then let's look here. Look at this. That looks around roughly, 28 or so seconds. So that's going to be your difference between the P and S. All right, 28 seconds. So now we get to go down here to this nomograph. Okay, let's find 28 seconds on here. So 20, 30, okay, so 28's about here, right here-ish. So now we have to convert that, right? Because remember, the table is asking us for distance in kilometers. So 28 seconds would be roughly, here's 200, there's 250, so maybe 230 kilometers. Okay, cool. And if we want to figure out, okay, what's going to be the magnitude here, right? We can also use the amplitude to calculate what will be the Richter magnitude. So let's do that now. All right, so 230 kilometers. So let's go back up here. Okay, so we wrote 28 seconds, which was equal to 230 kilometers. All right, so now we need to locate the millimeters of amplitude of the wave, of the S wave. All right, so here we can see S wave. Okay, so here you've got a ruler here that you can copy if you don't have a ruler at home. So now let's look at the amplitude here of our S wave. So to me, looks to be about 3 centimeters, right? 3 centimeters is about 30 millimeters. So let's go down here. Okay, find 30 millimeters. Okay, so here's 20, 50, right? So roughly here. And so you're going to put a dot there. You'll put a dot where we had the 230. You'll draw a line across, and where it intersects, that's the magnitude, right? The Richter magnitude of the earthquake. So that's what you're going to put in this box here. Okay. So I think you guys can do the next two, right? This one's a little bit trickier, right? It's not as clean as the top one. So go with your best possible guess. All right, so now the next part asks you to locate the earthquake epicenter. So let's say we decided, right, we found that the distance between P and S was 230 kilometers, right? That's one of the things we calculated, right, from the 28 seconds. Okay, so that would mean, here's our scale. All right, 230 is about here, right? So that distance here. That means that around this station bar, any direction, 230 kilometers in any direction, the earthquake epicenter could be, right? It basically says that there's a circle of a radius of 230 kilometers in which the earthquake epicenter could be, right? So that's the uncertainty, is that circle. So you're going to draw that circle, and it doesn't have to be, exact. If you don't have a compass at home, you can use a ruler and eyeball it. So you'll do that for each of these 3 stations, and then you're going to have 3 circles, right? And where each of these 3 circles intersect, that tells you their common point. So that's the location of the earthquake epicenter. All right, and then the last part has also been giving some people trouble. So on the Southern California fault map, right? So I gave you guys a link to this in the announcements, and I'll show you how to use it better. You're going to label the following faults. So here you've got a list of faults A through K. And you're going to have to label them on here. So all of these black lines are faults. The San Andreas is a fault. It's the big one. But there's lots of little individual splays or splinters off of the San Andreas. And so your job is to put names on all these faults, right? A through K. So now let's look at the geologic map that I've recommended. Before we do that, let's see if we can take a mental image of this picture. We have sort of four main stems. We got this fault stem, this fault stem, this fault stem, and this one out here in the Pacific Ocean. This one makes kind of a Y shape. You see that? This one next to the Y has lots of these tiny little, faults, very dendritic. And then this one's just more linear. Okay, so now let's go and look online at this California map. So either one will work. All right, so let's zoom in here now. Double click, or you can press this plus sign to zoom. Okay, now let's see if we can try to identify what we've seen in that picture, right? And maybe you're a little lost, and that's okay. So let's do a search. Let's look back here at our PDF and look for one of the faults that it's asking for. All right, how about the San Jacinto fault? Let's look that one up. Okay, so now we can see fault. Okay, that's good. We're on the right track, right? And here we go. Here's the San Jacinto fault zone. So now let's zoom out a little bit. All right, oh, I'm seeing some other faults here. Here's the Banning fault. Right? I think that's one of the ones that we're supposed to label. Here we've got the Mission fault, the Claremont fault. Here we have the Loma fault, the Elsinore fault. So let's zoom out here because it's starting to look a little familiar now. All right, where's that Y? Let's see if we can find that Y-shaped fault. So here we can see this Y. And remember, that looks just like the one from our diagram. And then next to it, there was one that looked very dendritic here. And then remember, we saw one also off in the ocean, right? Off in the Pacific Ocean. So let's zoom in. I'm curious which one that is. Oh, look, that's the Inglewood fault. Here's the Canyon fault. So you get to do a little bit of exploring, and you'll kind of have to flip back and forth from this picture to your lab. Where is it? You'll flip back and forth and say, okay, this looks more like this fault here, right? So that's why I'm giving you an extra week. It's a long lab, and I want to make sure that you guys are engaging and actually using these programs. Okay, so that's the geologic map that you can use to identify all the faults. And whoever can catch them all, if you get all of them, I'll give you a bonus point. Okay, so I think that's all that should help you. But if you have any remaining questions, don't forget you can always talk to me on the phone during my office hours. And I'm here to answer emails as well. Okay, good luck, guys.